Have you ever just stopped and wondered what's really holding up all of mathematics? Underneath the crazy equations and the complex geometry. Well, today we're going to do just that. We're going on a little expedition right down to the bedrock to find the absolute blueprint that everything else is built on. I mean, think about it. Math is everywhere. It's in your phone's GPS, it powers the entire internet, it even tries to predict the weather. But what is it? Like, really? We see the numbers and the symbols, but those are just the tools. The actual stuff of math, the atoms of its universe, they're way simpler and, honestly, a lot cooler than you might think. And that's our whole goal for this explainer. We're going to peel back all the layers, calculus, algebra, you name it, one by one, until we hit the absolute core, the single foundational idea that all of mathematics just blossoms from. So here's our game plan. First, we'll find these atoms of math. Then, we'll figure out how to describe them and compare them. After that, we'll build a language, the language of logic, so we can talk about them precisely. And finally, we'll see how this blueprint lets us build the entire universe of mathematics. Sound good? Let's go. All right, let's dive in. Section 1, the atoms of math. So if we took all of math and broke it down into its smallest, most fundamental piece, what would we even find? The answer is a set. That's it. It's not a number, it's not a shape, it's just, a collection. Seriously, think of it like a bag. You can put anything you want in this bag, numbers, letters, even other bags, as long as you have a clear rule for what gets to be in the bag. And the things we put inside, we just call them elements. Okay, so to speak this new language, we need a little bit of grammar. This symbol right here, in, that's our first word. It just means is an element of. It's a super precise, no confusion allowed way of saying, hey, this thing is in that collection. So, for example, the number 2 is an element of the set of even numbers, right? So we write 2 element of 2, 4, 6. But 2 is definitely not an element of the set of odd numbers, so we just draw a line through the symbol, n element. See? It's perfectly clear, there's just no room for misunderstanding. But what happens if our bag is empty? Now this is where it gets a little weird, but it's so important. In math, an empty bag isn't just nothing. It's a something. It's called the empty set, and it gets its own special symbol, phi. Think about the set of all dogs that can fly. That set totally exists, it's just empty. This idea of giving nothingness a formal name is one of the most powerful concepts in all of math. Okay, so we've got our basic building blocks, the sets. Now we need some rules for how to actually work with them. So on to section 2, describing and comparing. Turns out there are 2 main ways to describe what's in your set. The first way is super straightforward. You just list everything inside. We call that the tabulation method. The second way is a little more elegant. You just state the rule that an element has to follow to get in. And that's the rule method, which, as you can imagine, is a lifesaver for sets with, an infinite number of things in them. So how do we compare 2 different sets? Well, the main idea is this thing called a subset. Think of it this way. If you have 2 boxes, and literally everything in the first box is also inside the second box, then that first box is a subset of the second. It's really just a relationship of containment. Let's walk through a quick example. Let's say set A is just the numbers 3, 9, 12, and set B has the answers to the equation x squared equals 9. So B is 3 and negative 3. So is B a subset of A? Well, we just check. Is 3 an A? Yep. Is negative 3 an A? Nope. Okay, we can stop right there. Since not every single element of B is in A, B is not a subset of A. It's a really simple but totally foolproof process. All right, so we have our objects, sets, and we have a way to compare them. But to actually build arguments and prove things, we need a proper language. And that brings us to section 3, the language of logic. This is where we learn how to speak with absolute mathematical precision. So, the fundamental building block of this language is the statement. And a statement is just a sentence that has to be either true or false. That's it. There's no gray area, no kinda, no ambiguity. In the world of logic, it's all or nothing. And you can see the difference right here. 5 plus 2 equals 9 is a perfectly good statement. Why? Because we can say with 100% certainty that it's false. But something like x plus 1 equals 0, that's not a statement by itself. We can't say if it's true or false until we know what x is. And that distinction is the absolute bedrock of all logical thinking. Now, the most basic thing you can do in logic is just to negate something. If we have a statement, we'll call it P, its negation is not P. and we write it with this little symbol, not P. You can think of it like a light switch. If P is on or true, then not P is off or false, and vice versa. It's a perfect flip. Okay, now for the really fun part. We have these basic logical sentences, these simple true or false ideas. Now it's time to build with them. Welcome to Section 4, Compound Statements. This is where we learn how to connect simple truths together to create really complex and powerful arguments. This is like the mortar that holds our whole mathematical building together. And the process is actually really simple. You just take two basic statements, let's call them P and Q, you join them together with a special word called a connective, and bam, you get a brand new compound statement. And whether that new statement is true or false depends entirely on whether P and Q are true or false. It's like logical chemistry. So our first connective is and. The best way to think about and is like a super strict bouncer at a club. The statement P and Q is only let in. It's only true if both P are true and Q is true. If either one of them is false, the whole thing is false. The bouncer says no, no exceptions. Next up is or, and or is way more chill than and. The statement P or Q is true as long as at least one of them is true. It doesn't care which one. The only way for an or statement to be false is if both P and Q are false. And now for the big one, the most important connective of them all, if, then. Think of an if P, then Q statement as a promise. Let's say I promise you, if it rains, then I will bring an umbrella. Now, when is the only time I've actually broken that promise? It's if it rains, so P is true, and I don't bring an umbrella, so Q is false. That's the only time I lied. In every other scenario, my promise is still good. This simple idea is the engine that drives all logical deduction. Okay, we've gone from these simple little collections all the way up to the rules of logic. So what, right? Why does any of this actually matter? Well, that brings us to our last section, why this blueprint matters. This is where it all clicks into place. It matters because this isn't just a random collection of rules. It's a language. As the source material for this whole explainer puts it so well, this is the language that mathematicians use to present mathematical ideas. It's a system that was literally designed for absolute, perfect clarity. A way to build arguments so solid that you simply can't poke holes in them. So let's just zoom out and look at the blueprint we've uncovered. We started with the super simple idea of a set. We made rules to compare them, then we built an entire language, and or if-then, to talk about them with zero confusion, and it's this incredibly rigorous step-by-step process that allows us to build everything from your times tables all the way up to quantum mechanics. And we know with absolute certainty that the foundation is solid. That right there is the power of precision. And all of this leaves us with a really deep and kind of mind-bending question. We've built this entire mathematical language from scratch, right? Starting with our own definitions and our own rules. So is this language just a perfect mirror, something that's simply describing a reality that was already out there waiting for us? Or is it a creative act? Are we discovering the universe's blueprint, or are we in fact the ones drawing it? Something to think about.